In the last class we looked at the union find data structure. That was the data structure to maintain a collection of disjoint sets under the operations of union. That was the operation we were doing on the sets. That was the operation which was modifying the sets, yeah, or modifying the collection. And the find operation was just to identify, given an element, which set it belongs to, right. And we used this, we needed this data structure to implement Kruskal's algorithm, right. And Kruskal's algorithm was the first algorithm we looked at for computing a minimum spanning tree in a graph. It was an example of a greedy algorithm. Right. So today we are going to look at another algorithm for computing the minimum spanning tree in a graph. This one is due to Prim, and that's what we are going to discuss today. Okay. So let me define the notion of a cut in a graph first for you. So recall that we are talking of undirected graphs. A spanning tree, the notion of a spanning tree is defined only for a undirected graph. For a directed graph, there are different notions. We don't say a spanning tree in a directed graph, right. It is only an undirected graph we are talking about here. So I give you an undirected graph. A cut, let us say this is graph G, a cut in this graph G is a partition of the vertex set into two parts. What does it mean? Let me break the vertex set into two pieces. So let us say one piece is this and the other is the remaining, because it is a partition, right. So this way of splitting would define a cut. Okay. So if for instance I had vertices A, B, C, D, E, so then the first cut I am considering is A, B on one side and C, D, E on the other side, right. There could be many other cuts possible, right. I could have A, C and D on one side, A, C and D on one side, and B and E on the other side, yeah, why not. Or I could have only one vertex, let us say C on one side and the other 4 on the remaining 4 on the other side. These are all examples of cuts in the graph. How many cuts can there be in a graph? 2 to the power n? 2 to the n or something? 2 to the power n minus 1, because this partition is the same as saying C, D, E and A, B. How did you come up with the number 2 to the n? Every element, for every element there are two choices, either left or right, say, right. So there are 2 to the n different possibilities, but then we are repeating, each possibility is repeated twice, right. Once we will say A, B go on the left side and C, D, E go on the right side, and the other time we will say C, D, E go on the left side and A, B goes on the right side, but the partition is the same, yeah. So that is why number of different cuts. To the n minus 1. Minus 1 also? Oh, okay, the null, you are talking of the null. Chaliye. Okay. Okay, sometimes what we do is, when we say a cut, so cut is really a partition of the vertex set, but I sometimes would also say, or these edges which are going from one side to the other side are called the edges in the cut. Yeah. So these edges would be called the edges in the cut, edges in the cut or edges of the cut, whatever. You understand which edges am I talking about? Edges which have one endpoint in one side of the partition and the other endpoint in the other side of the partition. Okay. Great. So you understand what a cut is. We need this notion, and how do we use this notion? So suppose I take a cut of my graph, some cut in the graph S, and I will denote the other side by S complement or V minus S, where V is the vertex set, right. So, I have a graph G is V, the vertex set, and E the set of edges. So, S is the set on one side and the remaining is the set on the other side, right. And now, let me look at all the edges which are in the cut. Okay, recall we are trying to compute a minimum spanning tree. Okay, so, I am now going to be talking of a particular property of minimum spanning trees. So, let me take this cut and let me look at the edges in the cut and let us look at their lengths of these edges. So, maybe this edge is length 2, this is length 4, this is length 3, this is length 7. Okay. I am going to be assuming that all the edge lengths are distinct. This is just to ease all my arguments, to simplify my arguments, right. All the algorithm, everything works even when edge lengths are not necessarily distinct, right. So, just to simplify my presentation here, that I am going to assume edge lengths are distinct. Okay. Now, the claim is that, so recall when edge lengths are distinct, there is a unique minimum spanning tree. We have discussed this before. Yeah, there is one and only one minimum spanning tree. Now, the claim is that this edge, which has length 2, will be part of that minimum spanning tree. Okay. So, let me write down the claim more formally. For any cut S complement, the minimum edge in the cut belongs to the MST. ठीक है, समझ में आ रहा है। आप कोई भी कट ले लीजिए ग्राफ में, यही नहीं कोई भी ले लीजिए, बहुत सारे कट्स हैं आपके पास, 2 to the n-1 डिफरेंट कट्स हैं। कोई भी कट लीजिए, उसमें देखिए मिनिमम एज कौन सी है, वो वाली एज आपके मिनिमम स्पैनिंग ट्री में जरूर होगी। और भी हो सकती हैं, एक से ज्यादा एज हो सकती है मिनिमम स्पैनिंग ट्री में। ये जरूरी नहीं है कि केवल एक ही एज होगी मिनिमम स्पैनिंग ट्री में, एक से ज्यादा भी हो सकती है। नहीं समझ में आया, कैसे हो सकती है एक से ज्यादा? हाँ, हाँ, फॉर इंस्टेंस ये जैसे ये हमारा ग्राफ था, इसके अंदर लेट्स मेक अ ट्री सच दैट देयर विल बी बोथ ऑफ दीज एजेस विल बी पार्ट ऑफ द मिनिमम स्पैनिंग ट्री। तो किस तरह का मैं ट्री बनाऊं? मान लीजिए मेरा ट्री था ये मेरा ट्री था, both the edges are part of the minimum spanning tree. I could have my edge length so that this was the minimum spanning tree, right? I could choose my edge length so that this is the minimum spanning tree. So, it is not necessary that only that for any cut there is only one edge which is part of the minimum spanning tree. There could be more than one edges which are part of the minimum spanning tree. But all we are claiming is that the minimum edge in the cut will belong to the minimum spanning tree. तो ये जो एज है जिसकी लेंथ 2 है, दिस विल हैव टू बी इन द मिनिमम स्पैनिंग ट्री। अगर ये नहीं है मिनिमम स्पैनिंग ट्री में, तो आप कह सकते हो कि ये मिनिमम स्पैनिंग ट्री है ही नहीं। क्यों? वाई? व्हाट्स द प्रूफ? सो द प्रूफ इज बाय कॉन्ट्रडिक्शन। ठीक है, आपने एक स्पैनिंग ट्री लिया, आप कह रहे हैं कि यू आर सेइंग दैट दिस इज द मिनिमम स्पैनिंग ट्री, बट दैट ट्री डज नॉट कंटेन दिस एज। सो लेट T be a MST. MST is short for minimum spanning tree. So T is an MST which does not contain edge. इस एज को एक नाम दे देते हैं, E दे देते हैं इस एज को नाम, does not contain edge. So what now? What will I do?
So to have the vertices joining from this to this, we will use any of these vertices.
I will add E to the tree. Add E to T, what will happen? Cycle will be formed. Yeah. Why will a cycle be formed? Because these two vertices are already connected. These two vertices are already connected in the tree. Yeah. So there is some path going from this vertex to this vertex. Any path that goes from this vertex to this vertex, from U to V, which connects U and V, has to use one of the edges of the cut. है ना? Think of this as this is a river in between, this is one end, this is the other end. If you have to go from this end to the other, you have to use one of these bridges. No other alternative. So it has to use one of these edges, which means that the cycle that gets formed has to use one of these edges at least. But all these edges have length more than 2. So what will I do? Same thing. I will remove this edge from the cycle and add that. This will reduce the length of the tree. So let me write that down. So we'll add E to T. Let me continue. Right? So after you add E to T, so let me addition of E to T forms a cycle, say capital C. C contains at least one edge of the cut. Yes or no? Yes. At least one edge of the cut. So this implies C contains at least 2. Huh? It will contain an odd number of edges of the cut.
So now you added.
Okay, added C, at least one edge. Let me write down other than E. Good. E को अभी हम नहीं गिन रहे. E तो होगा ही होगा cycle में. E will have to be part of the cycle, right? Because it is because of the addition of E that the cycle got formed. There was no cycle earlier. So E has to be part of the cycle. So C contains at least one edge of the cut other than the edge E. So this implies C contains an edge of length more than the length of E. C contains an edge of length more than the length of E. What's
Can their length be greater than E?
There can be greater than E. I just have to show that there is some edge in the cycle which has length more than E.
So that we won't remove E from the cycle. We will be removing something else to resolve the cycle.
Right. No, we created the cycle, right? So we brought in E. Now how do we want to reduce the cost of the tree? By removing some other edge whose length is larger than E. By removing this edge from T union E, we get a smaller tree. Yeah, that's a contradiction because we assumed that T was a minimum spanning tree. नहीं समझ में आ रहा. ये हमारी जो साइकिल बनी इसमें एक ये एज E है और कोई और एज होगी कट की. एक तो होगी ही होगी. मान लीजिए वो एज F है. F की लेंथ E की लेंथ से ज्यादा होगी क्योंकि कट की सारी एजेस की लेंथ E की लेंथ से ज्यादा है. तो अब हम क्या कर रहे हैं, E को डाल रहे हैं और F को हटा दे रहे हैं. This we have discussed before that from a cycle I can remove any edge and it will remain a spanning tree.
Sir, if there were to be some other edge which is not a part of the cut but length greater than.
We can also remove that. I just have to show you that there is some edge in the cycle which can be removed. I have to just arrive at a contradiction.
How to be the edge in the cut?
I am just arriving at a contradiction here. This is a mind game. We are not actually removing anything, right? I am just proving a structural property. I am saying in any cut, the minimum edge has to be part of the minimum span. All of this, I don't ever sit down and remove anything. This no algorithm does that, right? This is just a proof, proving this statement, right? And इस प्रूफ करने के लिए आप कोई भी एज हटा सकते हैं उस साइकिल की जिसकी लेंथ ई से ज्यादा हो, पर आपको कैसे पता? हाउ डू यू नो दैट वन ऑफ द एजेस ऑफ द साइकिल हैज लेंथ मोर देन ई? Because we can only argue for the edges of the cut. For them we know for sure that they are all more than E. That's all, nothing more, right? Now how are we going to use this claim, right? That's so Prim's algorithm exploits this simple fact that if you take any cut, the minimum edge in the cut will be part of the minimum spanning tree always. Prim's algorithm is an algorithm which essentially is built around this simple fact. Okay? So let's understand what Prim's algorithm does. Let's say this were my what graph, and let's give every edge a length. So I'll just arbitrarily put down edge lengths 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12. Say I missed out one, 13. Now how does Prim's algorithm work? So first we start from some vertex and we call this the root vertex, right? Now the first partition that I am considering, the first cut I am considering is the root versus everyone else, right? Root on one side and everyone else on the other side. So which edge has to be part of the cut? The edge of length 1. So I'll include this into my cut, which edge has to be part of the minimum spanning tree, the edge of length 1, and I'll include it into my tree. Now what is the cut I am going to consider? This and this. So I am going to, this is going to be one side of the cut, this is going to be one side of the cut, and the other side of the cut is going to be all the other vertices. So which are the edges which are part of the cut? 9, 8, 2, 3, 11. So which is the smallest? 2. So we know for a fact that this has to be there in the minimum spanning tree. Just include it. Okay? Ab, what is the cut I am going to consider? These three vertices on one side and all the others on the other side. So let me extend it like that. Yeah? Can everyone see this? This is one side of the cut and all the other vertices are on the other side of the cut. So now which are the edges in the cut? 9, 8, 7, 5, 13, 11. 3 is not in the cut because both endpoints of 3 are on the same side. Yeah? So the smallest of these is 5. So this gets included. Now I am going to, you can now understand how I am going to extend it, right? This becomes my one side of the cut and the remaining becomes the other side of the cut. 4 is an edge, right? 3 is kind of gone. So 9, 8, 7, 6, 4, no, not 10, 13 and 11. Okay? So 4. और अब हमारा एक साइड ये हो जाएगा. अब which are the edges in the cut? 11, 13, 10, 6, 7, 8, 9. So 6 is the smallest, so it gets included. And now my set becomes this, right? It's time we finish because it's getting very messy. Yeah. So which are the edges in the cut now? Is 8 in the cut? No, right? It looks like it is in the cut, but it's not, because both its endpoints are on the same side. So it's 9, 10, 11, 13, also 12, of course. 9, 10, 11, 12, 13. So 9. Ab 12 is not in the cut anymore. So it's only 10, 11, and 13 are the options. So 10 is the smallest, and with that we are done, right? Because all the vertices are now included. Everyone understands the procedure, right? It's very simple, and we have done the proof effectively. Not effectively, we have done the proof, right? Because what did we say? We proved this claim that the minimum edge across the cut has to be part of the minimum spanning tree, and that's the edge we are picking at every point. So this is the minimum spanning tree. Okay, you'll get the same tree. Since this is unique, I assumed edge lengths are distinct. You'll get the same tree even if you were to run Kruskal's algorithm. Yeah, everyone follows this? So I'm not going to write down the pseudo code for this, but you understand how the algorithm works. Very simple. So the key idea is that we have, so let's try and see how you would implement this algorithm. So what is it that you have to maintain? So of course you have a data structure for the graph, right? Now what is it, what is the operation you have to do at each step? Add a vertex to a set. So at any point you have the following. This is one side of the cut. Your root is here. Let me call this the set S. So the set S is going to be the set on one side of the cut, as in the vertices that we have already reached, so to say, from the root. So the root is always part of the set S, and the remaining vertices S complement of V minus S, right. So I have to maintain this collection of vertices which are on one side, right. This can be done very easily by keeping one bit with every vertex. If the bit is 1, then that means let us say it is on the S side. If it is 0, it is on the S complement side. Yeah, that is very simple. Now what is it that I have to do at each step? I have to find out, I have to look at all of these edges and to find the minimum. How on earth am I going to do this? Yeah.
We can check all the edges which are connected and we can compare them to the already minimum which we have. So we can effectively keep pointer on the minimum edge outside, which is going out of the set S.
कैसे करेंगे? देखो, एक तो नई way is that you look at all of these vertices, you look at their adjacent edges, right? For each edge you see whether the other endpoint is in S or not. If it is not in S,
then check the length.
Then you look at its length and you look at all these edges and find the minimum. So how much does that time take? How much time does it take? Order? You're going to each vertex, looking at all its adjacent edges, right? Looking at all its adjacent edges. Going to each vertex in S, looking at all its adjacent edges. What is the maximum time it could take?
Order NM.
Order M at each step.
And
and you have n such steps, तो order m in time लग जाएगा. ठीक है? I'm not even writing it down because it's a very naive way of doing things. Yeah. So let's look at something clever. What would be a clever
From
way?
the previous step, the set that
Maintain a minimum.
you cannot maintain.
When you add a new vertex, compare the edges from that previous.
Okay, let's see. This is some idea. So you are saying I have the set S. I have S complement, and there is this vertex V. Let's call it V. Why have I singled this vertex out? Because this is the vertex which is now going to go from right to left. ठीक है? इस समय you have figured out the minimum of all of these edges. You know the minimum of these edges in the cut, right? Now what is going to happen? V, let me draw it this way now. Right? Some edges are going to go from V to S. Some edges go from V to S complement. There are of course some edges which go from S to S complement. Yes? Now, right now I know the minimum of these edges. Yes? Because V is on this side. This picture is the same as knowing the minimum of these edges. When I move V from here to here, I want to find out the minimum of these edges. What will I do? Compare the. So I just suppose I have just kept track of the minimum of these, nothing else. Huh? Right. So let's say the minimum was 1. The minimum has to be an edge incident to this one. That you understand? That's why we picked this one, right? So this is 1, this is 2, this is 5, this is 6, and this is 7.
We need the second minimum. Not the second minimum, it's a minimum not connected.
Right?
Which is not connected to the
And then these are
second minimum, which is not connected.
8, 9, 3, let's say. So now the new minimum, earlier the minimum was 1, and now the new minimum is 2. Yeah? So if I just know the minimum, it's not going to be useful. So you want me to keep track of the second minimum also?
Go from S to
Which does not go to? But what do I know about V? As in V is something that I find out, right, at this step?
Means ordered track, because we, suppose the next minimum also goes to V, or even if we have we keep up the second minimum which is not going to V, but then if after removing that what edge has been added, the third line which is going from there, we are not keeping a track of it, and all those edges can have the length more than that one, and if we don't keep a track of it, we have to again compare.
So we know the minimum that is coming to this vertex. So suppose we keep track of the minimum to each of the vertices in S complement.
So when we insert S inside,
Insert V.
inside S, then we can navigate all the edges incident on V, and we can keep marks for those which are completely inside S, which are edges in the cut and which are inside S complement.
Okay.
And then we can we'll take degree V time to traverse all the edges which are on V, and then we can consequently change them, and then we'll traverse the edges, the set of edges, so that we get how many all those edges which are in the cut, and then we can take the minimum every time.
Okay, so what he's saying is, but how to, so what data structure should I use to keep these edges? A heap. Huh? Min heap.
So we can keep it starting min till we get a useful edge, and then the next vertex that we add, we can add all the adjacent vertices to the heap and keep extracting it.
Okay, so that would be one possibility. I have a heap. Does everyone know what a heap is? So heap is a data structure in which I can put some elements. Each one of them has a certain priority or a certain key, and it will give me, I can use an operation called delete min, which will remove the minimum element. I can find out what the minimum element is in the heap in constant time. I can insert elements into the heap. I can also remove elements from the heap. I can do all of these operations, right? And except for find min, all operations take log n time. Find min takes constant time. Yeah, everyone remembers at least this much. Yes? Okay, good. So suppose I were to keep a heap here, a heap which contains these edges 2, 1, 6, 5, 7, right? Then using find min, I can find out what is the minimum edge. That will, once I know the edge, I know the other endpoint of the vertex. I know both the endpoints of the edge. I know which vertex I have to bring in. When I have to bring in this vertex, I look at all the edges incident at this vertex. The edges which are going in S, I have to remove them from this heap. And the edges which are going from this vertex to vertices not in S, I have to add them into the heap. Yeah?
So removing is not as necessary as for the order, because when you are finding the minimum, you can just check and remove at that point. If you remove the minimum and check whether it is completely inside S or it is an edge cut in the edge.
Yeah, but let's keep it clean. Like when we say that our heap is going to contain the edges of the cut, let it contain only the edges of the cut, right? Because you're going to spend the same amount of time in any case.
You have to first search the edge and then
You can't search it.
You don't search in a heap. Please remember, heap is a very bad data structure for searching. So how do you find out where the edge is in the heap? Once again, the same thing, right? When you put some information related to the edge into the heap, you don't just put it and forget it. You keep a track of where the information is, where that particular node is. We don't need to delete, but there's no harm in deleting also.
we have to delete min operation यार बीच में से delete
Which is making a cycle.
ये सारे नहीं left वाले.
Check whether it's making a cycle in constant time. and check at that time.
Sir, we only have delete min operation. We cannot delete an edge from between.
No, you can also delete from a heap. Why can't you not delete from a heap?
Delete only the minimum, right? But can we, if we can delete any element, then we can search that element, right? First we need to search it and then delete.
Okay, so there is some confusion here. Let me back up a little bit, right? So we need to, I think I'll need to show this delete operation to you again. So when we do our other class, we will do the delete operation once again. But take it from me that you can also delete from a heap in the same login time. Okay. Of course, to delete, you need to know where the element is. You're not searching for the element, right? You know where the element is, and then you can delete from the heap in login time.
You restructure only from that point.
Right. Okay. So that's what we are going to do. When this element comes in, I'm going to insert 3, 9, and 8, and I'm going to delete 1, 6, and 5, and I know exactly where 1, 6, and 5 are. Okay. And this is how I'll do the implementation. So at any point, what does the heap contain? Exactly the edges of the cut. Exactly those edges and nothing else. Right? It's best to keep it clean so that you know what's happening. Right? Now, how many operations are required on the heap? What kind? How many?
So degree of V into log n.
right? So let's look at our heap operations. So let me draw this picture again for you. This is vertex V. It's coming in. It's coming in on this side. So these edges have to be removed. These edges have to be added. Yeah. Each remove and add takes log n time. So how much time am I spending? Degree times log n for every vertex that I process. So degree of V times log n, right? And then this has to be summed over all the vertices, because I will process each vertex exactly once. ये log n number of elements in the heap, which could be m. So I should write log m. Number of elements in the heap, which is number of edges in the cut, could be as much as the number of edges, although it will never be that, but it could be as large as that in the worst case.
Sir, but when we are removing these many edges,
Yeah.
we are increasing, it cannot be in.
Yeah, we are decreasing, but you know those are so small that it will not going. You know, even if you do a careful analysis, you'll still get the same order. Yeah. So this is what the total running time would be. Right. These are not the only operations. I also have to do one find min. How many times do I have to do find min? Number of vertices times, n times, right? So वो भी अगर हम ऐड करना चाहें n into order 1 constant time. That's a small order term than this one. What else do we have to do? What are the other operations we might have to do on the heap? Just insert and delete, right? And this operation, find min. So everyone understands what the procedure would be now, right? You start with your initial vertex root, and all the edges incident to the root will be your initial heap, will be the elements of the initial heap. Then you will do a find min. That will tell you what vertex to include, right, on that side. Then you are going to look at all the vertices adjacent to this vertex, all the edges adjacent to this vertex, decide if you have to remove an edge or to add an edge. नहीं समझ में आ रहा, बहुत मिस्टीरियस लग रहा है. चलिए इसका फिर सूडो कोड लिखते हैं. बताइए कैसे लिखेंगे? Right, so let's say I have an array S. S is an array. S of V equals 1 if V belongs to S, 0 otherwise. What is this S? This S is the S side of the cut. Not visited but reached, all those vertices that have been reached. Yeah. So this is one data structure we are going to have. Then we are going to have a heap, right? And let's see what. So initially I pick a vertex as the root, and S of that vertex root equals 1, and for all V, S of V equals 0. So initially everything, this is my initialization, right? Only the root is on. So initially everything is 0 and S of R is set to 1. This is my root vertex. Now what should I do? I should insert the edges incident at the root into the heap. Yes. So what should I do? For all E incident to R, do h, that's my heap, dot insert e, some such thing, right. I have to insert the edge into the heap. Yes, so everyone follows what I'm doing. Yeah, good. तो ये इंसर्ट हो गई. अब मुझे क्या करना है? पहले मिनिमम निकालेंगे फिर लूप चलाएंगे. ओके, सो कब तक हमें लूप चलाना होगा? While not, I would say not h dot empty, right. जब सारे उसमें आ जाएंगे तो आपकी जो है हीप एम्प्टी हो जानी चाहिए. Do, now what should I do? I should find the minimum edge. H dot find min equals, let's say this is equal to, what will this return? This will return an edge. F बोल देते हैं इसको, ठीक है. And okay, now what should I do with F now?
For all edges that are
for only find the
अभी मुझे क्या पता चला है? मुझे बस ये पता चला है. अब मुझे क्या करना है? I have to find the endpoint of F which is not in S. Let V be the endpoint of F such that S of V equals 0. ये आप कर लेंगे. आप दोनों एंड पॉइंट को देखेंगे कौन सा 0 है कि नहीं, वो आप इस स्टेटमेंट में होगा. अब क्या करना है मुझे इसका?
for all edges that are going from
For all
W adjacent to
E,
adjacent to V.
E adjacent to V, do.
if
What
the,
do I do?
if the other endpoint is not visited, that is not equal to 1, is 1, then
So for all E equals V comma W कर देते हैं इसको, आसानी रहेगी, है ना. If S W equals 0,
then insert
तो वो कब होगा? ये W है आपका, ये V है, ठीक है. अगर ये 0 है तो इस एज को हमें हीप में इंसर्ट करना है. देन H डॉट इंसर्ट E, नॉट W. हीप में हमारे एजेस हैं, वर्टिसेस नहीं है, ठीक है. एल्स H डॉट ठीक है.
S of V को 1 ही कर सकते हैं.
इसके बाद करते हैं, यहाँ कर देते हैं, कोई बात नहीं. और कुछ? बेसिकली ये जो हमने F है, जो एजेस हमें मिली हैं, इनको हमें रखना पड़ेगा क्योंकि दिस इज द स्पैनिंग ट्री, द मिनिमम स्पैनिंग ट्री, राइट. सब कुछ कर दिया आपने, मिनिमम स्पैनिंग ट्री नहीं प्रिंट किया तो फायदा नहीं ना.
T equal to 5 and T equal to T.
हाँ, तो जो भी आप, यू विल जस्ट प्रिंट आउट दीज एजेस और व्हाटएवर इट इज, ठीक है. दिस एंटायर थिंग इज पार्ट ऑफ दिस फॉर लूप. क्लियर टू एवरीवन? कोई घबराने वाली बात नहीं थी ना? हो गया, चलिए, गुड. ठीक है, and as you can see all the effort is being spent in this step, or not too much actually in this step, right. How many times is this loop going to be executed?
M time.
M times? How many times is this loop, the while loop, going to be executed? N minus 1 or n times, n minus 1 times. Why? Because every time I execute this loop, one vertex comes into the set S. n vertices है, ऐसे तो है नहीं कोई vertex निकलती है इससे, right? So this is getting executed n minus 1 times. So this statement is executed n minus 1 times, but this is again just a constant time operation. So this is not too much time. ये तो छोटा सा है, ये भी constant time है. It is this where the most of the work is getting done. For every, you are looking at all the vertices adjacent to the vertex V, degree, and for each one of those vertices or edges, you are spending doing either an insert or a delete, log m, right. So degree times log n, we have seen that before, summed over all vertices will be m log m. Yes. There is a modification to this scheme that can also be done. In this modification, what you do is, you have your set S, you have your set S complement, right. Each vertex in S complement has a number on it. Each vertex in S complement has a number on it. What is this number going to be? Yeah, let us look at all the edges going from this vertex to S. Suppose these were the 3 edges going from this vertex V to S. Suppose these edge lengths were 3, 4 and 7. Then this vertex is going to have a number of 3 written on it. ठीक है, okay. And what are we going to do with these numbers? We are going to create a heap. Now my heap is a heap of vertices and not of edges. So this heap has one element for each vertex in S complement. हर एक वर्टेक्स के लिए एक यहाँ पे हमने एक एलिमेंट डाल रखा है, और उस एलिमेंट की प्रायोरिटी क्या होगी, इसके करस्पॉन्डिंग जो होगा 3 होगी, ठीक है. Yes. Now what will be the minimum element in the heap? It will be the vertex which has the minimum edge incident at it amongst all the edges in the cut. So it will be the vertex which has to go across. ठीक है, आ रहा है समझ में नहीं? So if I find the vertex, the vertex which is sitting here at the top, the vertex with the minimum value, minimum label, let's call these labels, the vertex with the minimum label, let's say it's this vertex, is पे label 1 था, right? So that means that the minimum edge going across this cut is 1. Yeah, we are not keeping track of edges which are here, within here. This vertex will only contain a label which is equal to the minimum of the edges which are going across the cut. If there is a vertex which has no edge going across the cut incident at it, इस पे कोई edge यहाँ से यहाँ नहीं जा रही है, तो इसका label हम मान लीजिए infinite रख देते हैं, ठीक है. So the minimum will tell me which is the minimum edge going across, and that's the vertex that I have to move across. And when I have to move across a vertex, what do I do? How do I update information? Very simple. This is the vertex V. अब ये vertex जब उधर जाएगा तो इस वर्टेक्स से जो एजेस यहां जा रही होंगी, किन को चेंज करना पड़ेगा? केवल इन वर्टिसेस के लेबल्स को चेंज करना पड़ेगा. ऑल दोज इन एस बार विच आर एडजेसेंट टू दिस वर्टेक्स. मान लीजिए इस एज की लेंथ 2 है, इसकी 6 है और इसकी 8 है, और इस पे लेबल 4 है, अभी इस पे 5 है और इस पे 7 है. तो इसका नया लेबल क्या होगा? इस पे 4 है लेबल, इसका क्या मतलब हुआ? द मिनिमम एज दैट इज कमिंग टू दिस वर्टेक्स सो फार is 4, but now this edge is also coming to this vertex because this vertex is going on that side. So इसका लेबल 4 से घट के 2 हो जाएगा. इसका लेबल, इसके ऊपर एक एज ऑफ लेंथ 5 आ रही है फ्रॉम हियर. ये वाली एज एक नई एज आ रही है अब इसके ऊपर, पर इसकी लेंथ तो ज्यादा है, तो ये इसका यही रहेगा. इसके ऊपर अब 7 आ रही है, अब एक जो आ रही है वो 8 है, तो इसका भी वही रहेगा. तो केवल इसका घटेगा. सबके समझ में आ रहा है ये? ठीक है. सो दैट्स द ओनली थिंग वी हैव टू डू नाउ. So what is the operation we have to do on the heap now? Update what? Update or decrease? We will only decrease the label. Decrease priority. Decrease priority is the operation we have to do. Right? हाँ, decrease priority के बाद जो भी heap अपने आप modify होगी वो होगी, और कोई ऑपरेशन नहीं करना है हमें. राइट? नो इंसर्ट, नो डिलीट. फाइंड मिन ऑफ कोर्स एंड डिक्रीज प्रायोरिटी. ये सबके समझ में आ रहा है? या? ओके. Since I have 4 or 5 minutes, let me write down the code for even this one. ठीक है, आज आपको खुश कर देते हैं, सब चीजों का कोड लिख के दिखा देते हैं. ठीक. So once again, as in the previous case, I'll have my array S. Yeah, and I'll do the same initialization for all vertex V. SV is initially 0, and S of R is 1. Okay. Now remember, the heap is going to contain vertices in S complement. Yeah. Heap is going to contain vertices in S complement. What should I put initially in my heap? Everything. Except R. Okay. So for all V, SV equals 0, and let's say I do H dot insert V comma, किस प्रायोरिटी के साथ इंसर्ट करूं मैं इसको? एक्चुअली हमें पहले भी प्रायोरिटी डिसाइड करनी चाहिए थी एजेस के केस में, पर वहां पे तो क्लियर था एज की प्रायोरिटी इज जस्ट इट्स लेंथ. यहां पे वर्टेक्स की प्रायोरिटी क्या होगी? डिस्टेंस फ्रॉम आर. व्हाट डज दैट मीन? व्हाट डज दैट मीन? Length of the edge from R. Infinity कर देते हैं सबको उठा के. ठीक है. और एस आर के लिए हम क्या करेंगे? हमने तो सारे वर्टिसेस को पहले इन्फिनिट कर दिया. Okay, H dot insert हाँ, तो ऐसे कर देते हैं. So इसको कर देते हैं H dot डिक्रीज प्रायोरिटी कर देते हैं, R कॉमा 0 कर देते हैं. ठीक है, पहले हमने सबको डाल दिया, केवल हमने R की प्रायोरिटी को 0 कर दिया. अब हम क्या करेंगे? No, no, no. Everything is infinite. Only R is 0.
सर अब R को तो एक निकालना पड़ेगा ऊपर का कंटेंट को ले लेते हैं
हाँ, अभी निकालते हैं, डरिए मत. So while H is not empty, we'll do something. What will we do? We'll take the minimum. Let's say that's a vertex V. Right? I'll take the vertex. तो अब ये क्या होगा? ये शुरू में जब आएगा तो ये कौन सा वर्टेक्स मिलेगा मुझे? रूट, क्योंकि उसकी मैंने प्रायोरिटी 0 डाली थी. अब मैं वो काम करूंगा कि उसकी एडजेसेंट एजेस को देखूंगा. तो अब वो करते हैं. तो अब हमें मिनिमम वर्टेक्स V मिला है. अब हम क्या करेंगे? इसकी सारी एडजेसेंट वर्टिसेस को देखेंगे. फॉर ऑल W adjacent to V, do. If W is adjacent to V, what should I do? If SW equals 0, what does that mean? W is on the S complement side. Then what should I do? Then I have to update its priority, right? Then if, what should be the new, what is the option here? If
label of W is greater than length of V comma W.
if, yeah, so we will need a label array somewhere. If label of W, so मान लीजिए एक हमारी label array भी है, right, which is keeping track of our labels. So if label W,
Greater than length of
so इसका label is greater than length of V comma W, then that means that this edge now, so what is this saying? इसके ऊपर अभी जो label था, मान लीजिए इसके ऊपर label 10 था और ये edge की length 6 है. इस edge की length is less than that label, that's what is being said. Then इसका label अब 6 हो जाना चाहिए. Then label W equals 6. Sorry, equals length VW and H dot decrease priority W comma label W. ठीक है, ये यहां खत्म हुआ, ये यहां खत्म हुआ, और कुछ नहीं करना है हमें. S of V को 1 कर देते हैं. चलिए, हाँ, पहले भी 1 कर दिया था. चलिए यहां नहीं करते, खुश रहिए. ठीक है. So this was an alternate way of doing it. It has the same running time complexity. You will check that yourself. Why is that? Because once again we are looking at degree. We are spending degree time for each vertex and degree times log n, because decrease priority also takes log n time, right? Sum over all vertices will become m log n, and that's basically where most of the work is getting done. Okay? So with that I am going to end today's lecture. So we looked at Prim's algorithm for computing minimum spanning trees, and we saw 2 ways of implementing it.